Popula- Population models are another example of compartmental analysis. So, for example, how do you model the growth of a population? If we're interested in a single population, we can think of the species as being contained in a compartment, like a petri dish, an island, a country, etc., and study the growth process as a one compartment system. If we let P of t represent the population at time t, then we can model dp dt by taking the birth rate and subtracting the death rate. Here's where we ignore immigration or emigration from a country. If we assume that those rates are proportional to the population, we get the following. dp dt is some constant times p. So let's call that k1 times p, that's the birth rate, and then we can subtract k2 times p for the death rate. And we can simplify this model by introducing a new constant k, and that constant is k1 minus k2, because it lets us rewrite this as k1 minus k2 times p, right? By factoring out the p. And so we replace this by k, new constant, and we get Malthusian or exponential law of population growth. dp dt equals k times p, where p at 0 is p naught, the starting population. Now, this is a separable equation, and the solution to this differential equation can be found as follows. We start out by multiplying both sides times dt, and then we get dp equals kp times dt. And now we can divide by p on both sides, and then we get 1 over p dt equals k dt. And then we can integrate both sides. Oops, on the left, I have dp, right? dp. And now I integrate both sides with respect to their variable. 1 over p dp. When I integrate that, I get ln of the absolute value of p. And on the right-hand side, I get k times t plus some kind of constant of integration. Now exponentiate with respect to e on both sides, and we get that the absolute value of p is e to the power kt plus c. And if I write this as a product, then I can get that p equals plus or minus e to the power c times e to the power kt. And I can give this another name. Let's call that constant k, whether it's positive or negative. It doesn't matter, it's still a constant. And so that gives me that p of t is a constant k times e to the power little k times t. So this is capital K. Now I have an initial condition. The initial condition is that p of 0 equals p naught. So when I use that, I plug that into my equation. I get P naught is K times e to the power K times 0. And so capital K, because this is going to be 1, I see that capital K is just P naught. And so my final model is P of t equals P naught times e to the power k t. Okay, so let's do an example with that. In 1790, the population of the United States was 3.93 million, and in 1890, it was 62.98 million. Using the Malthusian model, estimate the US population as a function of time. So, what I want to do here is I want to let t equals 0 in 1790. And what that means is that p at 0, the population at time 0, is the population in 1790. And so that's my p naught, and that's going to be 3.93. And so at this point, I know that my model looks like this. P of t equals 3.93 e to the power k t, and t is years since 1790. So 1890, that means that t is 100. So in 1890, t equals 100, and it means that p of 100 is 62.98. So p of 100, according to the model, is 3.93 times e to the power k times 100, and that is 62.98. So now I can divide both sides by 3.93, and then I get e to the power 100k equals 62.98 divided by 3.93. Then I take the natural log on both sides. I get 100k equals ln of 62.98 over 3.93. And then finally, I divide by 100, and I get that k equals ln 62.98 minus ln of 3.93 all over 100. And that gives me approximately equal to 0.027742. And my model now is P of t is 3.93 e to the power, and now I'm going to plug in that value for k, at 0.027742 t. That's my model for the US population. Now, let's see what that means if we have that model, and let's see how realistic that is. So I got my answer here, and let's see what happens if I plug in the value for, let's say, 2020. So in 2020, our T is 230, right? That's 230 years after 1790. And so if we plug that in into our formula here, we get P of 230 is 3.93 e to the power 0.02772 times 230. So E of 230. And the approximate value of that this is roughly 2320. Now, our units here are in millions, so this is million, or about 2.32 billion people. Now, that's a number that's way too big, so that really shows you the limitations of this model, where you have unchecked growth, and that is not something that is useful here.